Question 14a. A 0.25-meter long solenoid with a cross-sectional area of 5 times 10 to the power negative 3 meters squared has 100 turns of wire. The solenoid is connected in series to an open switch, 12-volt battery, and a 20-ohm resistor. The switch is closed. What is the rate of change of current when the potential difference across the resistor is 4 volt? So here in this question, we have a solenoid that has a length L of 0.25 meter, cross-sectional area as 5 times 10 to the power negative 3 meters squared, number of turns capital N as 100, potential difference of the battery VEMF is 12 volt, resistance R is 20 ohm, and potential drop across the resistor when the switch is closed is VR, which is 4 volt. We need to find what is the rate of change of current, dI over dt. So we will use Kirchhoff loop rule to solve this problem. This is how the circuit looks when the switch is closed. We will take the direction of current to be clockwise, and same will be the direction of traversing. Let us label the loop A, B, C, and D. So in this loop, as you go from A to B, you enter the negative terminal of the battery, so you write VEMF as positive. Then we are going in the same direction as current through the resistor, so we have to take potential drop across the resistor to be negative, so negative V times R. Potential drop across the inductor we will take as VL, and this VL must have polarity opposite to VEMF. Because the current through the circuit is increasing when the switch is closed, and the inductor does not want the current to change, so it introduces a back EMF that opposes the change in current. And the only way you can oppose the increase in current is when you reduce the power of the battery. And one way to reduce the power of the battery is to induce an EMF which is opposing the battery. So potential drop VL across the inductor we will take as minus VL, and all of this will be equal to 0. So we write this as VEMF minus VR. Potential drop across inductor can be written as L di over dt. So I write this as negative L di over dt, where L is the inductance and di over dt is the rate of change of current. Usually when we write this rule, we put a negative sign here. But since I already took the negative for potential drop across the inductor, we need not rewrite the negative sign again. Write this equal to 0. We need to find what is di over dt, so let's rearrange the term. I will move this to the other side. We get VEMF minus VR equals L di over dt. Now divide by L to calculate di over dt. We get di over dt equals VEMF minus VR over L. Now how do we calculate the inductance? Inductance L is given by the rule mu naught n squared L into A, where mu naught is magnetic permeability of free space, small n is the number of turns per unit length, L is the length of the solenoid, and A is the area of cross section. You can rewrite this as mu naught. Small n can be written as number of turns over the length L, and since it is a squared, we square the terms L times A. Then cancel off 1L from here, 1L from bottom. You get L to be equal to mu naught n squared A over L. So let's substitute that here. I get di over dt to be equal to VEMF minus VR. In place of L, we will write mu naught n squared A over L. Now we have everything to solve for this. So let's substitute the numbers. VEMF is 12, VR is 4, mu naught is 4 pi times 10 to the power negative 7, n is 100 squared, L is 0.25, area of cross section is 5 times 10 to the power negative 3, and when you solve this you get the rate of change of current to be equal to 31831 ampere per seconds. Now how can this question change? Suppose when the current reaches a maximum value, you open the switch. And when you open the switch, the current starts to decrease. In that situation, again we use Kirchhoff loop rule to write the expression for potential difference. But the only thing different over here is, since the current is decreasing, now the inductor does not want the change in current. It does not want the current to decrease. It wants the current to remain steady. So it tries to induces an EMF that supports the battery voltage, that is in the same direction or having the same polarity as the battery voltage. So in the situation when you open the switch, this VL we have written over here must have the same polarity as the battery. So instead of putting a negative sign here, we put it as positive. This is when the current is decreasing. But if it is increasing, when the switch is closed, you keep it as negative. Now let's discuss question 14b. A 0.50 meter long solenoid with a cross-sectional area of 4 times 10 to the power negative 3 meters squared has 200 turns of wire. The solenoid is connected in series to an open switch, 12-volt battery and a 20 ohm resistor. The switch is closed. What is the rate of change of current when the potential difference across the resistor is 9 volt? Again here we have a solenoid which has a length of 0.50 meter, area of cross section as 4 times 10 to the power negative 3 meters squared. Number of turns capital N is 200. VEMF as 12 volt. Resistance R as 20 ohm. And potential drop across the resistor as 9 volt. Again, we need to find the rate of change of current, which is di over dt. So we follow the same steps, show the direction of current I, show the direction of traversing to apply Kirchhoff loop rule. Again, since the current is increasing, potential drop across inductor has to be in polarity opposite to VEMF. So when I write Kirchhoff loop rule, I get VEMF minus VR minus VL equals 0. So we write VEMF minus VR. VL we will write as L di over dt equals 0. Move this to the other side. VEMF minus VR equals L di over dt. We need to find di over dt, so divide by L. Di over dt becomes equal to VEMF minus VR over L. Now L we found from the previous problem is equal to mu naught capital N squared A over L. And if you want to know how we got here, you can look at the previous problem in the video. So we rewrite this as di over dt equals VEMF minus VR over mu naught N squared A over L. Now let's substitute. VEMF is 12, VR is 9 over 4 pi times 10 to the power negative 7. N is 200 squared over the length, which is 0.5. Area of cross section is 4 times 10 to the power negative 3. And when you solve this, you get di over dt to be equal to 7460.4 ampere per second.